Hello, and welcome back to Silent Science World. Settle in, get comfortable, and let your eyes grow heavy, because tonight we are drifting out past the edge of everything familiar, into the deep, quiet dark, where the universe keeps its most astonishing secrets. Out there, among countless points of light, exist places and moments where the ordinary rules of the cosmos are stretched, twisted, and sometimes broken entirely. Tonight we will wander gently through some of the most extraordinary phenomena ever recorded by human instruments. The kind of events that can outshine galaxies, bend the fabric of space itself, and forge the very atoms that make up the ring on your finger or the blood in your veins. There is no need to follow every detail closely. You don't have to remember any of this. Just let the words wash over you, soft and unhurried, like starlight arriving after a journey of 1,000 lifetimes. If this kind of gentle, wandering exploration helps you unwind, feel free to leave a little note below or share this quiet corner of the internet with someone who might need a peaceful night too. But there is nothing you must do right now except breathe slowly, let your body sink a little deeper into whatever is holding you, and listen. Let's begin our journey among the stars. Somewhere in a galaxy much like our own, a single star is dying. And for a handful of days, it will shine brighter than every other star in that galaxy combined. Imagine billions of suns glowing together, and then imagine one dying star briefly matching that entire glow on its own. This happens when a star's internal furnace finally runs out of fuel and can no longer hold back the crushing pull of its own gravity. The core buckles inward at incredible speed, while the outer layers are thrown outward in a violent flash. For a short window of time, that flash can rival the combined brilliance of an entire stellar population. Then, gradually, over the following weeks and months, the light fades as the expanding cloud of debris cools and thins. Astronomers scanning the sky have caught these events by accident more than once, watching a seemingly unremarkable patch of a distant galaxy suddenly erupt with a single overwhelming point of light, only for that light to quietly disappear again. The star's ordinary existence gone forever. Now picture something even stranger. Somewhere out in the void, two collapsed stellar cores, remnants so dense that a thimble of their material would outweigh a mountain, are locked in a slow orbital embrace. These are neutron stars born from earlier explosions, and over millions of years they spiral closer and closer together, losing energy with every pass. Eventually, they collide. In that instant of impact, matter is flung outward under conditions so extreme that atomic nuclei can absorb neutrons faster than they can decay, building up some of the heaviest elements found anywhere in nature. In a single such collision, the resulting quantity of freshly minted gold could outweigh several planets the size of Earth. That glittering material doesn't stay bundled together. It disperses into the surrounding gas clouds, eventually becoming part of the raw material for future stars and worlds. So it's entirely possible that some of the gold sitting quietly in a drawer somewhere began its existence in the fiery aftermath of two dead stars smashing together in the depths of space. Not every stellar catastrophe requires an explosion at all. Consider a black hole quietly orbited by a wandering star that strays just a little too close. The star doesn't need to cross the black hole's boundary to be destroyed. Simple gravity is enough. The difference in pull between the near side of the star and its far side becomes so extreme that the star is stretched, pulled, and finally shredded, unable to hold itself together any longer. Instead of falling inward as one coherent object, it becomes streams of blisteringly hot gas. Part of that gas escapes into space on long, looping paths, while the rest swings back and begins circling the black hole, forming a rapidly spinning disk. As that gas collides with itself and heats up, it can release a tremendous burst of radiation, causing a previously invisible galactic center to flare dramatically into view. Astronomers have found these hidden black holes precisely because of this destructive event, watching quiet galaxies suddenly brighten in ways no ordinary star could explain. The black hole itself remains completely dark. What we see is only the wreckage swirling around it. Some flashes of light are so powerful that in a matter of seconds, they release more raw energy than our own sun will produce across its entire 10 billion year lifetime. These are known as gamma-ray bursts, and they rank among the most concentrated releases of energy the universe has ever produced. They aren't simply distant explosions appearing brighter than usual. They are highly focused events, tied either to the collapse of an extremely massive star or to the violent merger of two compact stellar remnants. Much of their radiation escapes through narrow, tightly focused jets, moving at speeds almost indistinguishable from the speed of light. If one of those jets happens to point directly at Earth, the burst appears spectacularly bright, even if it originated billions of light-years away. These flashes can be over before a telescope even has time to turn toward them, which is why automated satellites are constantly watching the sky, ready to alert observatories around the world the instant something extraordinary occurs. Let's slow down for a moment and consider the sheer strangeness of a neutron star itself. Take an object with more mass than our Sun and compress it down until it is roughly the size of a modest city. That is a neutron star. These objects form when a massive star's core can no longer resist gravity's pull, and the resulting collapse crushes ordinary matter into a state that doesn't naturally exist anywhere else on Earth. A neutron star might measure only about 20 kilometers across, and yet it can contain well over the mass of our entire Sun. Gravity at its surface is so overwhelming that anything dropped nearby would fall with a force utterly unlike anything experienced on our own planet, and the speed needed to escape its pull is a significant fraction of the speed of light itself. And yet, unlike a black hole, light can still escape from a neutron star's surface, which allows astronomers to study its heat and its spin. It occupies a strange middle ground in nature, matter pressed almost to the absolute limit of what it can endure without vanishing behind an event horizon. Now imagine two black holes, each already unimaginably dense, slowly circling one another across the emptiness of space. Their motion cannot be seen with any telescope, because they distort the fabric of space and time itself, sending ripples outward at the speed of light. These are gravitational waves. At first the orbit is slow and gentle, but as the black holes radiate away energy through those very ripples, their paths shrink, and the final moments of their dance become astonishingly rapid, spiraling faster and faster, until the two objects merge into one larger black hole. The resulting signal races outward across the universe, and by the time it reaches Earth, it has stretched and compressed space by an amount smaller than the width of a single proton, measured across detectors many kilometers long. The first confirmed detection of such a signal came from a collision more than 1 billion light-years away, and remarkably, nothing physically traveled from that distant event to Earth. Instead, the very geometry of space changed by an almost incomprehensibly tiny amount, and our instruments were sensitive enough to notice. Earth itself carries physical evidence of nearby stellar violence from long ago. Buried within ancient ocean floor sediments, scientists have discovered traces of a radioactive isotope that is extraordinarily difficult to produce naturally here on our planet. The most convincing explanation is that debris from a supernova explosion, occurring somewhere in our galactic neighborhood millions of years in the past, drifted across interstellar space and eventually settled onto the surface of our world. These explosions weren't close enough to cause any catastrophic harm, but researchers continue to investigate whether they subtly influenced our ancient atmosphere or climate. What makes this evidence remarkable is simply its existence at all, tiny physical fragments connecting our planet directly to the death of a star that vanished long before humans ever looked up at the night sky. Somewhere among the neutron stars scattered across our galaxy exist a rare and extreme subset known as magnetars, objects wrapped in magnetic fields so powerful that ordinary comparisons become almost meaningless. Earth's own magnetic field is strong enough to guide a compass needle and shield our planet from charged particles streaming from the sun. A magnetar's field can exceed that by factors reaching into the trillions. Near its surface, the field is powerful enough to distort the very structure of atoms. These fields are thought to arise from extreme conditions present at the moment the neutron star was born, although the exact details remain an active area of research. Occasionally, the immense stress stored within a magnetar's rigid outer crust becomes too much, and sudden rearrangements release enormous bursts of X-rays or gamma rays, briefly transforming a distant, otherwise unremarkable neutron star into one of the brightest objects in the observable sky. Not every dying star leaves anything behind at all. Most stellar collapses leave some sort of remnant, whether a neutron star or, for the heaviest stars, a black hole. But under very particular conditions, an exceptionally massive star can undergo something entirely different. Deep within its core, extraordinarily energetic light begins spontaneously producing pairs of matter and antimatter particles. This process removes the very pressure that had been holding the star up against gravity's pull. The core contracts violently, temperatures spike even further, and runaway nuclear burning takes hold. Rather than simply blasting away the outer layers, this reaction can tear the entire star apart, leaving nothing compact behind at all, neither neutron star nor black hole. Astronomers believe such stars were likely more common much earlier in the universe's history, when the raw material available for star formation contained far fewer heavy elements than it does today. Some of the ripples created by ancient cosmic collisions are, quite literally, still traveling toward us right now. A violent merger can end long before its gravitational waves finish crossing the universe. Once created, these ripples continue outward at light speed, growing weaker with distance, but never simply disappearing. This means detectors here on Earth can register disturbances that originated before our planet even existed in anything resembling its current form. When two distant black holes merge, their gravitational signal begins an unimaginably long journey while entire galaxies continue evolving around it. Billions of years later, that faint distortion may finally sweep past Earth, and our instruments capture only a fraction of a second of the strongest part of that ancient collision, hidden within which is detailed information about the masses and speeds of objects that vanished into a single larger black hole eons ago. The debris flung outward by a supernova doesn't simply drift away quietly. It can blast outward at thousands of kilometers per second, slamming into surrounding interstellar gas that may have been sitting relatively undisturbed for ages. Particles are heated to temperatures capable of producing X-rays, while nearby magnetic fields become compressed and tangled. As time passes, this shock wave gradually slows as it sweeps up more and more material, and the resulting structure can remain visible, spanning many light years, for thousands of years afterward. Some of the most famous remnants of this kind allow astronomers to watch this entire process continue to unfold long after the original explosion occurred, with different elements glowing at different wavelengths, revealing exactly how the interior of the dead star was thrown outward. One particular explosion remained visible in broad daylight for weeks. Ancient astronomers, watching the sky with nothing but careful eyesight, recorded a sudden new point of light appearing where no star had ever been noted before. Historical records describe a brilliant guest star that stayed visible during the day for more than 3 weeks and could be seen glowing at night for far longer still. At the time, no one understood they were witnessing the death of a distant star. Nearly 1,000 years later, astronomers connected those ancient written observations to a glowing, expanding cloud of gas occupying that exact same patch of sky, a cloud that contains, at its very heart, a rapidly spinning neutron star. It is a remarkable meeting point between written human history and modern astrophysics, proof that people living long before telescopes witnessed a genuine stellar catastrophe with their own eyes, and their careful notes are still helping scientists study the aftermath today. The collapse of a massive stellar core can unfold in less than a single second. A star's center may spend millions of years slowly evolving before suddenly undergoing a catastrophic transformation almost instantly. Near the very end of its life, the core becomes dominated by iron, an element that cannot release useful energy through fusion. With nothing left to hold the structure up, gravity finally wins outright. The core collapses at tremendous speed. Electrons and protons combine to form neutrons, and enormous numbers of nearly invisible particles called neutrinos are released. Once the innermost region reaches an extraordinary density, it suddenly becomes far more resistant to further compression. The collapse halts abruptly, and the core rebounds. This entire transformation can happen in a fraction of a second, though what follows afterward, as a shockwave attempts to push its way back outward through the rest of the star, remains a wonderfully complex puzzle that researchers continue to study using powerful computer simulations. Not every dying star explodes purely on its own terms. Some white dwarfs, dense stellar remnants left behind by stars that were never massive enough to undergo full core collapse, can spend billions of years quietly stable, only for a nearby companion star to change their fate entirely. In a close binary system, gravity can slowly draw gas away from that companion and onto the white dwarf. As the white dwarf gains material, conditions deep inside it can become increasingly extreme, until carbon fusion ignites explosively throughout much of the star. The result is a thermonuclear supernova that tears the white dwarf apart completely, leaving no conventional neutron star behind. What makes this kind of explosion remarkable is the sheer delay involved. A star can appear to have quietly finished its active life ages ago, only to become the center of a brilliant explosion because a companion elsewhere in the same system slowly altered its destiny. These particular explosions turned out to be extraordinarily useful scientific tools. Because their true brightness can be estimated with reasonable precision, astronomers can compare how luminous such an explosion actually was against how faint it appears from Earth, and use that difference to calculate distance across billions of light years. When researchers studying distant examples of this kind expected to measure how gravity was gradually slowing the universe's expansion, they found something completely unexpected instead. The explosions appeared fainter than predicted for a decelerating universe. The evidence pointed towards something astonishing. Cosmic expansion is not slowing down at all, it is accelerating. This discovery reshaped modern cosmology and led directly to the concept now commonly known as dark energy, the mysterious force behind that acceleration. The explosions themselves never explained what dark energy actually is, only that something is out there causing the universe to expand ever faster. Ordinary stellar fusion has a natural limit. Stars are capable of building progressively heavier elements deep inside themselves, but producing anything heavier than iron through normal fusion no longer releases useful energy. To forge many of the heaviest elements in existence, nature requires environments packed with free neutrons and enormous amounts of raw energy, conditions found during certain explosive stellar events. This mechanism, in which atomic nuclei rapidly absorb neutrons faster than they can decay, is responsible for building some of the heaviest and rarest materials in the periodic table. Modern evidence suggests that colliding neutron stars are a major source of this process, though certain rare stellar explosions may contribute as well. What is clear is that much of the periodic table could never have been assembled through calm, ordinary stellar burning alone. Some atoms, quite literally, required a cosmic emergency to come into existence. A supernova's physical footprint can last for tens of thousands of years after the initial flash has faded from view. In its earliest stages, the ejected material moves outward rapidly, sweeping up surrounding gas as it goes. Eventually, the amount of gathered material exceeds the mass originally thrown from the star, and the remnant slows into a more gradual phase, spreading across dozens of light years over time. Its appearance changes dramatically as it ages. Young remnants often glow strongly in X-rays because their gas remains extremely hot, while older remnants become vast, glowing shells traced by delicate filaments of cooler material. Eventually, the boundary becomes almost impossible to distinguish from the surrounding interstellar medium, meaning the exploded star has, in a very real sense, become part of the galaxy itself, its expanding remains continuing to carry matter and energy through the space between other stars for ages afterward. At the heart of that ancient guest star's remnant sits an object almost as remarkable as the explosion that created it, a tiny, rapidly spinning neutron star rotating roughly 30 times every single second. Each rotation sweeps beams of radiation across space, producing regular pulses that astronomers can detect across multiple wavelengths. Those pulses are so astonishingly regular that scientists can monitor even the tiniest changes in the star's rotation with remarkable precision. Surrounding it lies a glowing cloud several light years wide, continuously powered by a stream of energetic particles released from the spinning core. Nearly 1,000 years after the original explosion occurred, the collapsed heart of that dead star is still actively injecting energy into the debris that once belonged to its parent, an engine that never really stopped running. Long before telescopes existed, careful human observers recorded sudden stellar explosions using nothing but patient eyesight. Historical astronomers in various cultures tracked the sky closely enough to notice when a bright new point of light suddenly appeared where nothing had been recorded before, sometimes even noting how bright the object appeared and how long it remained visible. These ancient descriptions can now be compared directly against known remnants scattered across the sky, and in several cases the match is convincing enough to give modern researchers a fairly precise date for when the original explosion occurred. That historical information genuinely matters, because the age of a remnant helps scientists calculate exactly how quickly its debris has expanded and how its brightness has evolved over time. Long before anyone understood what stars actually were, people recognized that the supposedly unchanging heavens could still surprise them with sudden new lights, and their careful records became invaluable scientific data centuries later. Some explosions shine far brighter than ordinary supernovae because they receive a hidden second source of energy from within. In certain extraordinarily luminous events, astronomers suspect the newly formed neutron star at the center is an unusually fast-spinning magnetar. At birth, such an object can rotate incredibly quickly and hold an immense reservoir of rotational energy. As its powerful magnetic field gradually slows that spin, some of the stored energy can be transferred directly into the expanding debris of the supernova itself, keeping the explosion far brighter than radioactive decay alone would normally allow. This idea helps explain a class of explosions known as superluminous supernovae, capable of vastly exceeding the brightness of more familiar stellar deaths. The picture is still developing, but the underlying possibility remains remarkable. An object born inside an explosion may begin powering the very debris created by its own formation almost immediately. Some of the largest stars ever formed may die without leaving any central remnant whatsoever. Deep inside an exceptionally massive star, temperatures can become so extreme that energetic light begins converting into pairs of particles, stripping away the pressure that had been supporting the core against gravity. The interior contracts and heats even further, and runaway burning can release enough energy to completely blow the star apart. No neutron star survives, and no black hole forms immediately from the destroyed core. Astronomers have searched for possible real-world examples of this kind of explosion by studying unusually luminous events and their unique chemical fingerprints. These particular giant stars are thought to have been rare in the modern universe, but may have played a much larger role in the earliest stages of cosmic history. Not every massive star announces its death with a brilliant flash of light. Sometimes the core collapses so powerfully that the outward blast simply never succeeds. Material continues falling inward until a black hole quietly forms, and if most of the star follows along, the expected explosion may never appear at all. Astronomers have searched for these so-called failed supernovae by repeatedly photographing enormous numbers of massive stars in nearby galaxies over long stretches of time, watching to see whether any of them simply vanish without ever producing the expected final flash. Several intriguing candidates have already been identified. If these quiet disappearances turn out to be common, they could help explain why observers see fewer ordinary explosions from the most massive stars than earlier models of stellar evolution once predicted. There is a genuinely beautiful cycle hidden within stellar death. When a supernova shockwave sweeps through a nearby cloud of cold interstellar gas, it suddenly places that gas under intense pressure. Regions that were previously too thin and diffuse to collapse under their own gravity may become compressed just enough to begin pulling together, eventually fragmenting into smaller clumps that can go on to form entirely new stars. This doesn't happen after every explosion, since the timing and distance both need to be favorable, but observations of expanding gas bubbles and active star-forming regions suggest that this kind of triggered birth does occur around energetic stellar remnants. The newborn stars may even contain material expelled by the original explosion itself. One generation of stars ends by violently rearranging the gas around it, and that very disturbance can help assemble the next generation. Stellar death, it turns out, is not simply an ending. Under the right conditions, it becomes part of the machinery that helps build new suns. Much of a supernova remnant's most dramatic light is completely invisible to human eyes. When an expanding blast wave strikes surrounding gas, particles are heated to temperatures of millions of degrees, stripping away many of their electrons and producing intense X-ray radiation. Space telescopes can separate this radiation into different energy bands, revealing exactly which elements are present within the debris. Oxygen might dominate in one region, while silicon or iron appears in another, allowing astronomers to reconstruct how the original destroyed star was layered internally, and even trace clumps of material that were launched outward in different directions during the explosion. Images built from this radiation look completely different from ordinary visible light photographs, because they reveal the hottest, most energetic components of the wreckage, rather than what an eye would actually see. The initial flash of a supernova is not the only reason it continues shining. Inside many explosions, the extreme temperatures create unstable radioactive isotopes, one particularly important example decaying step by step into stable iron, releasing energy at each stage in the form of particles and high-energy radiation. The expanding cloud of debris absorbs much of this energy and converts it into visible light, which can sustain the glow for weeks or even months after the original shockwave has already passed through the star. Astronomers carefully study how the brightness fades over time, because the pattern of that fading reveals which particular isotopes are powering the slowly dimming remnant. In some cases, radioactive decay dominates the light curve so completely that the underlying physics of unstable atomic nuclei becomes directly visible across the distance of an entire galaxy. During the earliest moments of stellar collapse, one of the very first warning signs escapes in the form of nearly invisible particles called neutrinos. These particles interact so weakly that trillions pass through your body every single second without leaving any noticeable trace. Yet during stellar collapse, they are produced in truly astonishing numbers. Because they can pass through the overlying layers of the star far more easily than ordinary light, they escape well before the visible explosion actually reaches the surface. In February of 1987, underground detectors on Earth recorded a small burst of these particles arriving from the direction of a nearby satellite galaxy. Hours later, astronomers watched a supernova ignite in that very same region. Only about 24 individual particles were detected across several separate experiments, and yet those few particles fundamentally transformed astrophysics, confirming that most of the energy released during a stellar collapse escapes as neutrinos rather than as visible light. It remains the only such explosion from which neutrinos have ever been directly detected, though modern instruments are now sensitive enough that a similarly nearby event today could reveal thousands of signals. After certain massive stars explode, their crushed remains can become some of the most reliable natural clocks in the universe. A pulsar is a rapidly rotating neutron star whose magnetic axis is usually tilted away from its spin axis, meaning charged particles accelerate around its magnetic poles and produce beams of radiation. As the star spins, those beams sweep through space like a rotating lighthouse, and if one happens to cross Earth, telescopes register a pulse each time the star completes a rotation. These objects were first discovered decades ago, when radio astronomers noticed an oddly repeating signal of astonishing regularity, so unexpected that researchers briefly wondered whether they had stumbled upon an artificial transmission. Nature soon offered a far more elegant explanation as more examples turned up. Today, astronomers know thousands of these spinning beacons, and their timing is precise enough to help study gravity, map the invisible plasma scattered between the stars, and even detect unseen companion planets by the subtle way their gravity tugs the pulsar back and forth. Some pulsars are regular enough that scientists can predict the arrival time of their pulses with remarkable accuracy, and tiny departures from that prediction can reveal extraordinary things. A pulsar might be orbiting a hidden companion star, moving through curved space, or experiencing subtle shifts in its own rotation. In fact, some of the very first planets ever confirmed outside our solar system were discovered exactly this way, detected purely through the way their gravity shifted a distant neutron star's timing. Interstellar gas along the path also leaves its mark, since different radio frequencies travel through ionized material at slightly different speeds, and correcting for that delay tells astronomers about the matter scattered between the stars. A seemingly simple, repetitive signal becomes, in the right hands, an extraordinarily precise experiment stretching across light years. The fastest known pulsars complete hundreds of full rotations every single second, their surfaces moving through space at a genuinely significant fraction of the speed of light. These objects, sometimes called millisecond pulsars, were not necessarily born spinning this quickly. Many were likely accelerated later in life by slowly stealing gas from a companion star, a process that gradually transfers momentum and spins the old neutron star up to remarkable speed. There is a physical limit to how fast such an object can rotate before material at its equator would no longer remain gravitationally bound, and studying the very fastest known pulsars helps scientists probe the strength and internal structure of neutron star matter, conditions that push far beyond anything a laboratory could ever recreate. The outer solid layer of a neutron star may be the strongest known material anywhere in nature. Unlike any crust found on an ordinary planet, gravity compresses atomic nuclei into astonishingly dense structures while electrons move through the material under immense pressure. Computer simulations suggest this crust might be roughly 10 billion times stronger than steel when measured by resistance to breaking. That doesn't mean it could ever be usefully mined or transported. Such matter exists only because crushing gravity maintains those extreme conditions, and removing it from that environment would cause it to change catastrophically and instantly. This incredible strength matters because a rotating neutron star can support tiny irregularities rather than becoming perfectly smooth and spherical, and those irregularities may generate continuous gravitational waves if the star spins quickly enough. What astronomers casually refer to as mountains on a neutron star might rise only a few millimeters or perhaps a few centimeters above the average surface. That sounds almost perfectly smooth, and yet the distortion still matters enormously, because a neutron star contains more mass than our entire sun, meaning even a microscopic departure from a perfect sphere involves a genuinely enormous amount of matter. If the star spins rapidly, such a tiny bump could cause its gravitational field to vary slightly with every single rotation, in principle creating a continuous stream of gravitational waves. Detectors around the world are actively searching for these extremely faint signals from known pulsars, hoping a successful detection would reveal information about the star's interior and show exactly how much strain its crust can actually endure. A teaspoon of neutron star material would weigh billions of tons. This staggering density comes from what happens when atoms are crushed far beyond their familiar form. In ordinary matter, most of an atom's volume is essentially empty space between its tiny nucleus and the surrounding electrons. During stellar collapse, pressure becomes so intense that electrons are forced much closer to the nuclei, and many combine with protons to produce neutrons instead. The resulting material ends up packed at densities similar to what's found inside atomic nuclei themselves. Such a sample could never simply sit on a kitchen counter. Outside the neutron star's crushing gravity, the material simply wouldn't remain in the same state. The comparison is useful precisely because it illustrates just how dramatically stellar collapse transforms ordinary matter. And remarkably, a neutron star maintains this incredible density across an object that is many kilometers wide, its entire interior compressed into exotic states of matter that physicists are still working to fully understand. Pulsars usually slow down very gradually as they lose rotational energy over time. Every so often, though, some of them do the exact opposite, suddenly jumping to a slightly faster spin rate in an event astronomers call a glitch. The change itself may be tiny, yet precision timing makes it completely unmistakable. One leading explanation involves a strange superfluid material believed to exist deep inside the neutron star, capable of flowing without ordinary friction. As the outer crust gradually slows down, tiny internal vortices within that superfluid may remain temporarily stuck in place, creating a growing difference between the rotation of the crust and the hidden fluid beneath it. Eventually, large numbers of these vortices shift suddenly all at once, transferring momentum outward and causing the crust to spin faster. Glitches offer one of the only ways scientists have to probe processes happening deep inside these otherwise inaccessible collapsed stars. A magnetar's magnetic field is never perfectly static. As it shifts and changes, it can twist and strain the rigid crust beneath the star's surface, which may resist for years before suddenly fracturing in what researchers call a starquake. Unlike an earthquake here on our own planet, this disturbance occurs on an object whose gravity and magnetism dwarf anything found anywhere near Earth. The resulting quake can rearrange magnetic structures outside the star and accelerate enormous numbers of particles, releasing bursts of X-rays or gamma rays. Some of these bursts last only a fraction of a second, while much rarer giant flares can release vastly more power. What begins as stress inside a crust only a few kilometers across can ultimately become a flash of light, visible from clear across the galaxy. In December of 2004, an enormous pulse of gamma radiation swept through our entire solar system, originating from a magnetar located tens of thousands of light-years away. The very first fraction of a second was so intense that it overwhelmed detectors aboard several spacecraft. Even at that extraordinary distance, the the radiation reached Earth strongly enough to measurably affect our upper atmosphere. This region, which normally responds most noticeably to activity from our own sun, was disturbed by a distant neutron star instead, a striking demonstration of the flare's astonishing power. Researchers concluded that an enormous rearrangement of magnetic energy had taken place on that far-off object. Had the exact same flare occurred much closer to home, its consequences would have been considerably more severe. Instead, our planet received nothing more than a harmless, measurable ripple from clear across the galaxy, a star only a few kilometers wide briefly reaching across an enormous stretch of the Milky Way to gently touch our own atmosphere. Why some neutron stars become magnetars while others do not remains one of the great open mysteries surrounding these objects. One influential idea centers on the final moments of the parent star's life. If the collapsing stellar core happens to be spinning extremely quickly, violent internal motion within the newly forming neutron star may amplify its magnetic field dramatically within mere seconds. Other explanations suggest some parent stars already possess unusually strong magnetic fields that simply become intensified further during collapse. Astronomers continue to compare magnetars against ordinary pulsars, studying the star clusters where some were born and examining nearby supernova remnants for clues about the original explosion. The question matters because magnetars represent a genuinely rare branch of stellar evolution, one where two seemingly similar massive stars can produce wildly different outcomes. A newborn neutron star begins its existence unimaginably hot, its interior potentially reaching temperatures of tens or even hundreds of billions of degrees immediately after collapse. And yet it sheds heat with remarkable efficiency, largely through neutrinos escaping from deep within during its earliest stages. Over thousands of years, the surface temperature falls dramatically, though the exact cooling rate depends heavily on what kind of matter exists in the interior, since certain nuclear reactions can release neutrinos very efficiently while unusual superfluid states can change how heat moves through the star altogether. Astronomers compare the measured temperatures of these stars against estimates of their ages, and a star cooling either faster or slower than expected can reveal hidden physics occurring many kilometers beneath a completely inaccessible surface. Deep inside a neutron star, matter may enter a genuinely strange quantum state with no everyday equivalent. Under enormous pressure and sufficiently low temperature, neutrons are believed to pair up and form a superfluid capable of moving without the ordinary friction that slows normal liquids. Similar behavior has been created in laboratories under extremely low temperatures, but neutron stars provide a natural version involving nuclear matter under crushing density. This superfluid doesn't simply swirl like water in a glass. Its rotation organizes itself into countless tiny quantized vortices threading through the star's interior, and their interactions with the surrounding crust may help explain sudden shifts in a pulsar's rotation. This strange internal state also affects how the star cools and how it emits neutrinos, meaning quantum mechanics itself may quietly govern the behavior of matter across an entire collapsed star. Just before a neutron star's solid crust gives way to its much deeper interior, matter may arrange itself into bizarre shapes that physicists have jokingly nicknamed after food. At these extreme densities, two powerful forces compete directly with each other: nuclear attraction trying to bind particles together, while electrical repulsion tries to push similarly charged regions apart. The resulting compromise may produce sheets, rods, and tangled structures rather than neat, simple nuclei, and researchers use playful names because the simulated shapes genuinely resemble familiar noodles and layered pasta. Behind the humor lies serious physics, since this material could be among the strongest configurations found anywhere in the universe, potentially influencing how heat moves through the crust and how the star's magnetic field evolves over time. A neutron star's solid surface isn't necessarily exposed directly to open space. Gravity can hold an extraordinarily thin but optically important layer of atmosphere above it, and because heavier elements sink rapidly, that uppermost layer often ends up dominated by the very lightest available material. The exact composition matters enormously when astronomers try to interpret the star's light, since different atmospheric elements shape the outgoing radiation in different ways, changing scientific estimates of the star's true temperature and size. Something as seemingly delicate as a thin layer of gas resting above a collapsed star can, in the end, significantly influence our best attempts to understand what lies deep inside it. Long before instruments could directly measure gravitational waves, astronomers found compelling indirect evidence through a pair of orbiting neutron stars discovered decades ago. Because one of the pair emitted precisely timed radio signals, researchers could track its orbit with exceptional accuracy over many years. According to general relativity, such a system should gradually lose energy by radiating gravitational waves, causing the two stars to spiral slowly closer together and complete each orbit slightly faster over time. Years of careful observation showed exactly that predicted behavior unfolding, with the orbital period shrinking at precisely the rate general relativity predicted. No detector had yet felt an actual gravitational wave directly, and yet these distant stars were clearly losing exactly the correct amount of energy. The discovery earned its researchers science's highest honors and stood as a beautiful example of nature itself testing fundamental physics decades before humanity built technology sensitive enough to catch the waves directly. For years, astronomers suspected that short bursts of gamma rays originated from colliding compact objects, and that suspicion became dramatically stronger when gravitational waves from a merging pair of neutron stars were detected in 2017. Less than 2 seconds after that gravitational signal arrived, satellites recorded a brief burst of gamma rays coming from the very same patch of sky. Telescopes soon located a rapidly changing point of light in a nearby galaxy. For the very first time, completely different kinds of cosmic messenger had traced back to the exact same event. Because these narrow beams point in only one direction, many similar collisions elsewhere in the universe will simply never point toward Earth, which is exactly why gravitational wave observations have become so valuable, capable of revealing collisions that gamma-ray telescopes alone might otherwise miss entirely. On a night in August of 2017, gravitational wave observatories detected a signal unlike any of the black hole mergers recorded before it. This one lasted noticeably longer and matched the unmistakable signature of two neutron stars spiraling together. Astronomers rapidly shared the estimated location with observatories all across the globe, and within hours, telescopes found a brand new point of light shining in a distant galaxy. Over the following days, nearly every branch of astronomy joined the investigation at once, with radio telescopes, optical instruments, and X-ray observatories all tracking different pieces of the aftermath. This single event marked the true beginning of multi-messenger gravitational wave astronomy, since information arrived through both ripples in space-time and ordinary electromagnetic radiation simultaneously. Researchers used the observations to test the speed of gravity itself, study the production of heavy elements, and investigate the behavior of impossibly dense matter, one collision suddenly connecting scientific fields that had often worked in isolation from one another. After two neutron stars collide, the radioactive debris thrown into space can create a faint, glowing transient, known as a kilonova, considerably dimmer than an ordinary supernova but carrying remarkably rich information within its rapidly shifting colors. Freshly created heavy nuclei are unstable and begin decaying almost immediately, and that radioactive decay heats the expanding material, powering the light astronomers observe. In its earliest moments, a kilonova can appear relatively blue, but as the debris expands and its composition becomes more influential, the emission tends to shift toward red and infrared wavelengths. Certain heavy elements are especially important here, since their complicated atomic structures make the expelled material highly opaque to visible light. By tracking exactly how this color evolves, astronomers can estimate what kinds of atomic nuclei were produced and how much material actually escaped the collision. Watching decades-old theoretical predictions about element formation quietly play out across another galaxy. Gold captures the imagination, but it is only one member of a much larger family of heavy elements that can emerge from neutron-rich cosmic wreckage. Platinum is another. During a neutron star merger, atomic nuclei can absorb neutrons in extremely rapid succession, faster than radioactive decay can pull them back towards stability, allowing matter to climb into regions of the periodic table that ordinary stellar fusion could never reach on its own. As these unstable nuclei eventually decay, they populate a whole range of stable heavy elements, platinum group metals included, with the exact mixture depending on the density, temperature, and neutron richness of the ejected material. Scientists compare theoretical predictions against kilonova observations and against the chemical fingerprints preserved inside extremely old stars that carry evidence from earlier generations of cosmic violence. A metal prized today for resisting corrosion may owe its very existence to matter once violently expelled from two colliding stellar corpses. The collision itself is not necessarily the final chapter of a neutron-star merger. What remains at the center depends heavily on the combined mass involved and on the precise physical properties of ultra-dense matter. If the merged object proves too heavy for any neutron star to support, it may collapse almost immediately into a black hole. In other cases, rapid rotation can temporarily help resist gravity's pull, allowing the remnant to survive for milliseconds, seconds, or potentially much longer before eventually collapsing anyway. If its mass remains below the relevant stability threshold, it could persist as an extraordinarily massive neutron star wrapped in an intense magnetic field, essentially behaving like a newly formed magnetar. These different possible outcomes matter enormously because a long-lived central remnant can inject additional energy into the surrounding debris, while rapid black hole formation tends to produce a noticeably different pattern of radiation. Each merger, in a sense, becomes a natural test of exactly how much mass neutron star matter can withstand before gravity finally wins completely. Some of the most spectacular structures produced by these compact collisions are narrow jets of matter racing outward at speeds approaching the speed of light. To launch one, material falling toward the newly formed central object first collects into a hot, rapidly spinning disk. Powerful magnetic fields threading through that disk can channel enormous energy along its rotation axis, driving a tightly focused outflow. Particles within that jet can move so close to light speed that relativistic effects begin to dominate everything an observer sees, concentrating radiation strongly in the forward direction and appearing to compress time intervals for anyone watching from a distant telescope. The jet has to force its way through debris left over from the collision itself, and if it succeeds, it produces intense high-energy emission before eventually creating a slowly fading afterglow as it plows into the surrounding gas. Watching that afterglow brighten and fade allows astronomers to reconstruct the geometry of an explosion that occurred impossibly far beyond any telescope's direct resolving power. Orientation alone can completely change how an extreme cosmic event appears from Earth. When material within a jet moves close to the speed of light, relativity concentrates much of its radiation directly along its path of travel, meaning an observer positioned near the jet's axis sees a source that looks dramatically brighter than someone viewing the exact same event from off to the side. This effect, known as relativistic beaming, helps explain why certain active galaxies appear extraordinarily luminous, and why some gamma-ray bursts remain visible across truly immense distances. The underlying source doesn't actually radiate equally in every direction. Geometry alone determines whether our planet happens to sit inside that narrow cone of enhanced emission. Sometimes the entire difference between an overwhelming cosmic beacon and a modest, easily overlooked distant object comes down to nothing more than which way its jet happens to be pointing. Certain gamma-ray bursts have been detected from distances so vast that their light began traveling when the universe itself was still remarkably young. These events matter precisely because their brief brilliance can cut clean through unimaginable cosmic distance. High-energy satellites first pin down a rough location, and ground-based telescopes then race to capture the burst's rapidly fading afterglow. If astronomers manage to obtain a spectrum in time, they can measure exactly how strongly the expanding universe has stretched that light toward longer wavelengths, and some bursts have been confirmed at distances corresponding to well over 13 billion years of light travel time. That makes them valuable probes of an era when the very first generations of stars and galaxies were still forming, since a single burst can briefly advertise the presence of one dying star with extraordinary intensity, even when the surrounding galaxy itself would otherwise be far too faint to study directly. The link between longer gamma-ray bursts and the deaths of massive stars became clear once astronomers found supernova explosions emerging from beneath several fading burst afterglows. The leading explanation involves a massive star whose core collapses while the rest of the star is still falling inward, creating a compact central engine capable of launching narrow relativistic jets straight through the surrounding stellar material. If one such jet successfully punches through the outer layers and happens to point toward Earth, we detect a powerful burst of gamma rays. The surrounding star can still go on to explode as an unusually energetic supernova after shedding much of its outer hydrogen and helium. Not every similar explosion produces a detectable burst, since the jet might fail entirely or simply point somewhere else. But the association gives astronomers a direct, physical link between certain high-energy transients and the final moments of particular massive stars. For decades, the much shorter cousins of these bursts proved considerably harder to explain. They flashed for less than about 2 seconds and often appeared far from any obvious region of active star formation, a distribution suggesting older stellar populations rather than young, recently formed giants. The strongest explanation eventually became the merger of compact remnants, especially pairs of neutron stars, binaries capable of surviving for millions or even billions of years while their orbits slowly shrink, often traveling far from wherever their original stars were actually born by the time they finally collide. Gravitational wave observations eventually provided decisive support for exactly this picture. What makes the phenomenon so remarkable is the sheer contrast in timescales involved. A binary can evolve almost invisibly for longer than complex life has even existed on our own planet, only to release its single most obvious signal in less time than it takes to speak a sentence aloud. The most important thing about many of these bursts isn't simply how powerful they are, but rather where all that energy actually goes. Because much of the radiation concentrates into narrow jets instead of spreading equally in every direction, a burst could technically occur fairly close by and still look completely unremarkable from Earth if neither jet happens to point our way. Astronomers might instead only notice an ordinary supernova, a faint kilonova, or a subtle afterglow produced as the outflow slows and spreads with time. This creates a significant observational bias, since the bursts we most easily detect are simply the ones whose beams happen to sweep directly across our planet. Researchers try to estimate this hidden, unseen population by studying jet angles and searching for later emission that only becomes visible once a beam widens with time, reminding us that genuine cosmic violence can occur surprisingly close by without ever producing its most dramatic signature in our sky. Some gamma-ray bursts last less than the blink of an eye, beginning and ending before a person could consciously react to them at all. Satellites have recorded flashes lasting only a tiny fraction of a second, which forces astronomers to extract an astonishing amount of physics from an extremely brief interval of data. Such extreme brevity tells researchers that the region producing the initial radiation must itself be remarkably compact, since a source simply cannot coordinate a rapid brightness change across an area larger than light itself could cross during that same interval. This kind of structure points strongly toward engines built on the scale of compact stellar remnants rather than ordinary stars. Other gamma-ray bursts behave in the completely opposite fashion, continuing to radiate high-energy light for hours at a stretch, hinting that their central engine can remain actively powered for far longer than researchers once assumed, exposing the underlying behavior of these central engines over a much greater span of time than typical bursts allow. A gamma-ray burst's visible flash may vanish within mere seconds, yet the explosion often keeps announcing itself at other wavelengths for days, weeks, or even months afterward. A relativistic outflow eventually crashes into gas surrounding its source, driving a shock through the material and accelerating charged particles that radiate across a wide swath of the electromagnetic spectrum, X-rays often dominating early on, followed by optical and radio emission fading more gradually over time. This fading afterglow actually gives astronomers far more information than the initial burst alone, since its spectrum can reveal the object's distance, its changing brightness can expose the shape of the jet and the density of its surroundings, and sudden fluctuations may indicate additional energy being supplied from deep within the central engine. Because the afterglow continues evolving, astronomers frequently coordinate telescopes right around the world in order to capture its different stages, turning a single momentary flash into a lingering scientific record that can be studied long after the initial explosion has faded from view. On one particular occasion in October of 2022, satellites detected an event so extraordinary that astronomers immediately gave it a memorable nickname, informally calling it the brightest of all time. Its gamma radiation was intense enough to completely saturate instruments specifically built to handle powerful cosmic flashes. and even detectors never designed primarily for gamma-ray astronomy still noticed clear effects from the event. The burst originated billions of light-years away, yet its jet happened to point exceptionally close to Earth's line of sight, an alignment that dramatically amplified its apparent brightness. Researchers studying the event across the full electromagnetic spectrum found evidence linking it to the collapse of a massive star, and it even measurably affected Earth's upper atmosphere despite the enormous distance separating us from its source. Statistically, an event this bright in our own sky may be exceptionally rare on any timescale a human might witness, and its detection gave astronomers an unprecedented natural laboratory for studying these relativistic jets while beautifully demonstrating how dramatically orientation alone can transform the apparent power of a distant explosion. High-energy radiation doesn't need to physically strike a planet in order to alter its atmosphere. X-rays and gamma rays can strip electrons away from atoms and molecules high above a planet's surface simply by being absorbed there, and if a sufficiently energetic cosmic explosion occurs nearby, this kind of ionization can temporarily reshape atmospheric chemistry. Here on Earth, strong gamma-ray events have measurably disturbed our upper atmosphere, even when their sources sat far beyond our own solar system entirely, and a much closer explosion could plausibly produce far larger effects, potentially altering ozone concentrations and allowing more ultraviolet light to reach the surface for a time. This certainly doesn't mean gamma-ray bursts routinely threaten inhabited worlds, since the dangerous combination of proximity and precise alignment should be genuinely uncommon. Still, the underlying physics reveals a fascinating connection between distant stellar catastrophes and the delicate chemistry of planetary atmospheres light-years away. A gamma-ray burst can act like a temporary searchlight, shining through material that would otherwise be almost impossible to examine directly. As the burst's afterglow passes through gas along its path toward Earth, atoms absorb very specific wavelengths of light, and astronomers can spread the incoming light into a full spectrum to identify exactly which wavelengths are missing. Each absorption feature reveals something about the material lying between the explosion and us, and for extremely distant bursts, that material can belong to an era when the very first generations of galaxies were actively transforming the young universe. This technique proves especially powerful because a single burst can briefly outshine its entire host galaxy by an enormous factor, and because these sources don't remain active for millions of years the way quasars do, they end up probing environments tied to individual massive stars rather than entire long-lived structures. For a brief window of time, the death of one remote star can effectively backlight billions of years of cosmic history, exposing matter that would normally remain almost completely invisible. Locating exactly where a burst occurred often requires hunting down its rapidly fading afterglow, since the initial gamma-ray detection alone frequently only narrows things down to a broad patch of sky. X-ray telescopes typically narrow the position first, and optical observatories then search for a new point of light absent from earlier images of that same region. Once the source is pinned down precisely, astronomers can determine whether a host galaxy lies beneath it, transforming an anonymous flash into a genuine physical event complete with a measurable distance and environment. Sometimes the host galaxy turns out to be astonishingly faint, only becoming visible once the afterglow has nearly disappeared entirely. This entire pursuit has essentially turned fading light into a form of cosmic detective work, the explosion itself often impossible to resolve directly, yet its vanishing afterglow pointing back precisely toward the exact place where the original catastrophe occurred. Most stars can safely orbit a massive black hole for immense stretches of time, provided they remain far enough away. Trouble only begins when an unlucky orbit carries a star inside the black hole's tidal radius, the critical distance at which the difference in gravitational pull across the star becomes stronger than the star's own ability to hold itself together. This critical distance depends on both objects involved, since a larger star can be disrupted farther out, while a denser star might survive a somewhat closer approach. The star may have drifted onto this dangerous path after gravitational encounters with other stars gradually altered its orbit over millions of years. Nothing needs to physically strike the black hole. The entire encounter is purely gravitational in nature. Once disruption begins, the star's previously orderly structure rapidly unravels, sending its material along an entire range of new trajectories. And astronomers search the centers of galaxies for the resulting flares precisely because many central black holes normally sit completely dormant and dark. Near a black hole, gravity changes dramatically over surprisingly short distances. During a close encounter, the side of a star facing the black hole feels a noticeably stronger pull than the far side, while the star is simultaneously squeezed inward along directions perpendicular to its orbit. The combined effect can stretch the star into an extraordinarily elongated stream of gas, a process sometimes nicknamed spaghettification, though the more precise underlying concept is simply tidal force. The star's original spherical shape disappears entirely as different regions acquire different orbital energies, some gas racing ahead while other material trails behind. Computer simulations show these streams wrapping around the black hole before colliding with themselves and beginning to circularize, converting orbital motion into heat and helping build an accretion disk. What began as one intact star can therefore become a structure extending far beyond its original size, its destruction caused not by physically touching the black hole, but purely by gravity pulling different parts of the very same object onto radically different paths. Being torn apart by a black hole doesn't necessarily mean every last piece of the unfortunate star gets consumed. During disruption, different portions of the stellar material receive different amounts of orbital energy, with some debris becoming more tightly bound to the black hole, while other portions gain enough energy to escape entirely. The bound material travels outward along elongated paths before eventually swinging back toward the point of closest approach, and its rate of return strongly shapes how the resulting flare evolves over time. The unbound fraction instead heads outward and can eventually mix with gas elsewhere in the galactic nucleus. This division produces one of the strangest possible outcomes imaginable: a black hole capable of completely destroying a star without actually consuming the whole thing, transforming what was once a single coherent object into separate populations of debris headed toward entirely different futures. The stellar debris that manages to escape capture doesn't simply remain parked quietly beside the black hole. Some of it leaves the encounter traveling at tremendous speed, and because different parts of the original star acquired wildly different energies, this unbound gas may be launched outward from the galactic center on trajectories that never return. This escaping stream carries elements that once belonged deep inside a star, and it can eventually collide with surrounding interstellar material, generating shocks and radio emission long after the brightest phase of the disruption has already faded. Its chemical composition also carries information about the destroyed star itself, since if deeper stellar layers were exposed during the encounter, resulting spectra might reveal products of nuclear processing that would normally stay hidden inside a star's interior. A tidal disruption event, then, does considerably more than simply feed a black hole. It can redistribute stellar material throughout an entire host galaxy. One close gravitational encounter separating a star into matter destined for permanent darkness and matter, thrown outward into an entirely new existence. Many galaxies harbor massive central black holes that remain remarkably difficult to detect directly. If very little gas happens to be falling inward, the black hole produces almost no radiation of its own, and it may sit completely dormant for centuries or much longer while nearby stars quietly orbit around it. Then, occasionally, one star wanders into danger, and the resulting disruption supplies a sudden reservoir of infalling material, causing the galactic nucleus to brighten dramatically. Astronomers can discover these flares through optical surveys, ultraviolet telescopes or X-ray instruments, and the light typically evolves gradually over months rather than remaining constant the way a persistently active galactic nucleus would. That temporary behavior helps identify the event, and once recognized, the flare can reveal information about the mass of the central black hole and the physics of matter falling toward it. A black hole invisible to ordinary observation may therefore end up exposing itself entirely through the misfortune of a single unlucky star. Most tidal disruption events glow simply because stellar debris heats up as it settles around a black hole, but a rare few do something considerably more dramatic, launching powerful relativistic jets directly from the galactic center. One well-known example erupted in X-rays over a decade ago and remained violently variable for an extended stretch of time, with the leading explanation involving a star being disrupted by a massive black hole while a jet happened to point roughly toward Earth. Exactly how such jets form remains under active investigation, though strong magnetic fields threading the newly formed accretion flow are almost certainly important. The jet can transport energy far beyond the immediate region of the destroyed star, generating radio emission as it plows into surrounding gas. And because relativistic beaming so greatly enhances a jet, viewed head-on, only a small fraction of these jetted disruptions likely look spectacular from Earth's vantage point. These particular events manage to combine two genuine extremes in a single system: a star torn apart by raw gravity, and then some of the energy released by that very destruction channeled into matter moving almost as fast as light itself. Not every close encounter with a black hole ends in total destruction. A star can pass near enough to lose only part of its outer layers before escaping onto a highly elongated orbit, and if that orbit remains gravitationally bound, the star eventually returns for another pass, each close approach potentially stripping away a bit more material and producing another flare. Astronomers have identified repeating transients that may be produced by exactly this kind of partial disruption, offering something genuinely rare in the study of transient astronomy: the chance to watch the same doomed star return to danger again and again, rather than witnessing a single catastrophe only once. The timing between these repeated outbursts offers information about the surviving orbit, while changes in brightness reveal how the star itself is evolving after each encounter, hinting that a black hole can sometimes behave less like a single fatal trap and more like a slow gravitational machine, repeatedly removing pieces of the very same star over successive passages. White dwarfs can also be torn apart, but only by a very particular class of intermediate-sized black hole. A white dwarf is so extraordinarily compact that an ordinary supermassive black hole would typically swallow it whole before tidal forces ever had the chance to destroy it outside the event horizon. A smaller black hole changes that calculation considerably. Intermediate mass black holes are thought to occupy the gap between stellar remnants and the true giants found at galactic centers, and if one happens to encounter a white dwarf, the tidal radius can lie safely outside its event horizon, meaning the compact star could actually be pulled apart before ever crossing the point of no return. Such an encounter might compress and heat the white dwarf strongly enough to trigger nuclear burning under certain circumstances, potentially producing an unusual, explosive transient, and detecting one would be genuinely exciting, since intermediate mass black holes have historically proven notoriously difficult to confirm through any other method. The famous boundary known as the event horizon is defined by the fact that nothing inside it can ever escape, yet the actual experience of approaching that boundary depends enormously on the black hole's overall mass. For a relatively small stellar mass black hole, the horizon itself is quite small, meaning gravity changes very rapidly across the length of any extended object nearby, and the resulting tidal forces can become destructive well before the horizon is even reached. Around a truly supermassive black hole, the situation is surprisingly different, since its horizon is much larger, allowing the gravitational gradient right at the boundary to be considerably gentler. An object could, in principle, cross the horizon of a sufficiently massive black hole without being immediately torn apart at that exact location, with the actual destruction occurring only somewhat deeper inside. This reveals precisely why black holes can't be understood by surface gravity alone. What actually matters for stretching an object apart is how quickly gravity changes from one point to another, meaning smaller black holes can end up being more violently disruptive near their horizons than considerably heavier ones, despite possessing far less total mass overall. There's actually a point at which making a black hole heavier makes a visible tidal disruption event less likely rather than more. As a black hole grows, its event horizon expands more quickly with added mass than the tidal disruption distance does, meaning that above a certain scale, an ordinary star can cross the horizon while still remaining largely intact. With any later destruction occurring somewhere, its light can never escape to tell the tale. Spin can shift this boundary somewhat, allowing disruptions around slightly heavier black holes under certain orientations. This creates a genuinely useful observational clue, since confidently identifying a tidal disruption flare emerging from a very massive galactic nucleus can help constrain that black hole's underlying properties. The absence of flares at the highest masses doesn't mean the black hole has somehow become too weak to destroy stars, only that its horizon has grown so large that the crucial moment of destruction has simply vanished from the observable universe entirely. During the final moments of a black hole merger, an extraordinary fraction of the entire system's mass can leave without ever becoming ordinary matter or light. In the very first directly detected merger, the two original black holes carried roughly 36 and 29 times the mass of our Sun, while the resulting final black hole contained about 62 solar masses, meaning around 3 suns worth of mass had effectively been carried away entirely as pure gravitational wave energy. For a brief moment, the power radiated in gravitational waves alone actually exceeded the combined visible light output of the entire observable universe. This certainly doesn't mean 3 actual stars were somehow destroyed. Mass already present within the orbiting black holes was simply converted into energy through the changing gravitational field itself. And measuring that missing mass lets physicists rigorously test numerical predictions of general relativity under some of the most extreme gravitational conditions nature has to offer. A newly merged black hole doesn't always remain exactly where its collision occurred. Gravitational waves can carry momentum as well as energy, and if those waves happen to be emitted more strongly in one particular direction than another, the final black hole must recoil in the opposite direction to conserve momentum, an effect commonly called a gravitational kick. Simulations show that certain configurations can produce recoil velocities reaching thousands of kilometers per second. In smaller galaxies, a sufficiently powerful kick could theoretically launch the black hole completely out of the system entirely, while a weaker recoil might simply leave it oscillating back and forth through the galactic center before eventually settling down again. Astronomers search for possible real-world examples by looking for active black holes whose positions or velocities appear noticeably different from those of their host galaxies, a remarkable consequence of 2 invisible objects merging, sending space-time ripples unevenly across the cosmos, and propelling the resulting black hole through space like an enormous gravitational rocket. The strength of this recoil depends heavily on just how asymmetrical the merger turns out to be. If 2 identical, non-spinning black holes approach in a perfectly symmetric configuration, their gravitational wave emission can balance out so completely that very little net momentum gets carried away. Change the masses, however, and that symmetry breaks down, creating a more uneven radiation pattern and a considerably larger kick. Spin can amplify this effect dramatically, especially when the 2 spin directions are arranged unfavorably relative to the orbit. Understanding these kicks genuinely matters for galaxy evolution, since small, early galaxies may have struggled to retain their growing central black holes if mergers frequently launched the resulting remnants away entirely. The massive black holes seen at the centers of galaxies today may therefore carry a hidden history of exactly which mergers they managed to survive. If a merger gives a black hole a substantial kick without fully ejecting it, that object can begin a long, slow journey wandering through its host galaxy. Rather than sitting quietly in the nucleus, it may travel thousands of light years outward before gravity eventually turns it back, with repeated passages gradually losing energy through interactions with surrounding stars and matter, slowly drawing the black hole back toward the center over an extremely long stretch of time. During this wandering phase, the black hole might carry along a tightly bound cluster of stars or a small amount of accreting gas, potentially making the displaced object detectable through those companions. A wandering supermassive black hole would genuinely challenge the tidy, familiar picture of every galaxy having its largest black hole fixed neatly at the center, reminding us that galactic nuclei can be dynamically messy places, where a merger from millions of years earlier may leave its central object still roaming the galaxy long after the original gravitational waves have already swept past Earth. The very final stage of a stellar mass black hole merger unfolds far faster than the events leading up to it are easy to imagine. The binary system itself may have existed for millions or billions of years, yet during its last moments within range of ground-based detectors, the orbital frequency rises rapidly as the black holes circle each other faster and faster while their separation shrinks, producing the characteristic rising signal astronomers call a chirp. Near the very end, they can complete multiple orbits in mere fractions of a second before their separate event horizons finally combine into one distorted remnant. This brevity is precisely why gravitational wave observatories often record these signals as short, sweeping pulses rather than long, drawn-out astronomical events, and sophisticated computer models are required to reconstruct exactly what happened from these fleeting vibrations. A binary can spend nearly its entire existence slowly approaching catastrophe, only to complete the most violent portion of its history before a human listener could even finish saying the word collision. After two black holes merge, the newborn object isn't immediately a perfectly settled, calm black hole. Its horizon has been violently distorted by the collision, and like a struck bell, the remnant responds by oscillating in characteristic patterns while radiating away those distortions as gravitational waves, a final stage astronomers call the ringdown. The analogy proves genuinely useful, since a bell's tone depends on its shape and material, while a black hole's allowed vibration frequencies depend entirely on its own physical properties. This signal fades rapidly as the object settles toward the stable state predicted by general relativity, and though ring-down waves are considerably weaker than the loudest part of the merger itself, making them challenging to measure with real precision, future detectors should be able to observe them with far greater clarity. Scientists are especially interested in determining whether several distinct vibration modes can be identified within that final signal, since if their frequencies match theoretical predictions for a genuine black hole, the result would offer an incredibly demanding test of Einstein's theory. General relativity makes an extraordinary prediction about any fully settled black hole. Once surrounding disturbances have completely faded away, an isolated astrophysical black hole can be described almost entirely by just its mass and its spin, with electric charge remaining negligible for any realistic cosmic example. Its ring-down frequencies therefore act somewhat like a fingerprint. Carefully measuring the pitch and damping of those gravitational wave oscillations lets physicists infer the mass and spin of the newly formed remnant. Detecting multiple distinct ring-down modes at once would offer an even more powerful test, since every single one of them ought to point toward the exact same underlying black hole properties. This entire program is sometimes compared to spectroscopy, since scientists are effectively identifying characteristic modes much the way astronomers identify chemical elements through spectral lines, except that instead of analyzing light from atoms, they are analyzing vibrations in space-time itself. When entire galaxies merge, their central black holes can eventually form a binary pair whose orbit spans distances vastly larger than anything found in stellar mass systems. Such enormous pairs move relatively slowly, meaning the gravitational waves they produce have extremely low frequencies, with a single wave cycle potentially taking years or even decades to complete. Detectors on Earth simply cannot measure signals like this using kilometer-long laser instruments, since the wavelengths involved are far too enormous. Astronomers instead use the entire Milky Way itself as part of the experiment, relying on scattered millisecond pulsars scattered across the galaxy as exceptionally stable natural clocks. If a long gravitational wave passes between Earth and those distant pulsars, it slightly alters the arrival timing of their radio pulses, and while the effect is genuinely tiny, monitoring many pulsars over years can reveal correlated patterns stretched across the entire sky. In this sense, the detector itself becomes galactic in scale, potentially tracing pairs of supermassive black holes orbiting one another in galaxies hundreds of millions of light-years away. After years spent watching some of the most stable pulsars in the sky, several international research collaborations recently reported compelling evidence for a shared gravitational signal oscillating at extraordinarily low frequencies. Researchers didn't detect one single sharp merger the way ground-based observatories typically do. Instead, they found slow variations in pulsar timing showing exactly the kind of spatial correlation expected from a genuine background of overlapping gravitational waves, with different pulsars affected in related ways depending on their angular separation across the sky. Detecting this subtle pattern required observations stretching across many years, since each individual wave changes extraordinarily slowly. This result opened up a completely different gravitational wave window from the one previously used to study stellar mass black hole mergers, allowing scientists to investigate processes operating on scales that had previously been entirely inaccessible. The leading explanation for this newly measured, extremely low-frequency background isn't a single enormous source at all, but rather the combined murmur of countless supermassive black hole binaries scattered throughout the universe. Galaxy mergers naturally bring central black holes together, and after two galaxies combine, their black holes gradually sink toward the new shared center and begin orbiting one another. Across the entirety of cosmic history, enormous numbers of systems may have reached this exact stage, their individual waves overlapping by the time they reach Earth and creating one persistent blended background rather than easily separated individual signals. The precise strength and shape of that background can reveal how frequently galaxies actually merge and how efficiently their central black holes manage to spiral together toward final coalescence. As pulsar timing measurements continue improving, astronomers hope this smooth background will eventually begin resolving into particularly loud individual binaries, a collective cosmic hum slowly separating into identifiable individual systems. A collision between two entire galaxies sounds as though it should involve billions of stars smashing directly into one another, yet in reality, direct stellar impacts are extraordinarily unlikely, simply because galaxies consist mostly of empty space. Even in the most crowded regions, the distances between individual stars remain enormous compared with their actual size. When two galaxies pass through one another, their stars usually continue along altered paths without ever physically colliding at all. Gravity does the genuine damage here, with each galaxy pulling on the other and altering the orbits of countless stars simultaneously, pushing some onto wider paths while flinging others into long streams extending far beyond the original galaxies. Gas behaves quite differently, since its clouds can genuinely strike and compress one another as the two systems overlap. The entire encounter may last hundreds of millions of years, with the galaxies passing through each other more than once before finally settling into a new form. From a distance, the result can look violently tangled, while on the scale of individual stars, most of the participants never come remotely close to actually touching. A spiral galaxy rarely keeps its elegant shape forever. When another galaxy approaches, its gravity can pull strongly on the disk, distorting the arrangement of stars considerably, with spiral arms stretching, bending, or becoming much more pronounced as the encounter unfolds. In some cases, a close passage creates broad bridges of material connecting the two galaxies, while other regions get pulled outward into sweeping structures that can remain visible long after the closest approach has already passed. This transformation unfolds slowly by human standards, yet it can completely reshape the appearance of both galaxies involved. Astronomers can run these interactions forward using computer simulations, comparing the resulting structures against real systems observed through telescopes, allowing researchers to reconstruct exactly how certain distorted galaxies may have originally formed. Galactic architecture, it turns out, is never truly fixed. The elegant shapes captured in astronomical photographs are only temporary stages within a much longer gravitational history that can include repeated encounters stretching across billions of years. Our own galaxy is not growing in complete isolation. Smaller satellite galaxies orbit the Milky Way, and some are gradually being pulled apart by its gravity even now. One nearby dwarf galaxy providing a particularly striking example as repeated passes around our galaxy strip away its stars, stretching them into enormous streams that wrap through our galactic halo. Astronomers can identify these former members by measuring their motion and their chemical composition, while other stellar streams reveal the remains of entirely different systems disrupted much earlier in the past. This ongoing process is sometimes called galactic cannibalism, even though it happens purely through gravity rather than anything resembling ordinary feeding, with a smaller galaxy slowly losing its identity as its stars become mixed into the larger one. Evidence scattered throughout the Milky Way's outer halo suggests many such mergers have already occurred over its long history, meaning some stars near our own sun may have actually been born in entirely different galaxies before eventually being absorbed into our own. Our nearest large neighboring spiral galaxy is currently approaching us, rather than drifting away with the rest of cosmic expansion. Careful measurements of its motion show that the two galaxies are gravitationally bound to one another and expected to interact several billion years from now, though the exact sequence of events remains somewhat uncertain, since small differences in sideways motion could still change how the encounter ultimately unfolds. Current models generally predict at least one close passage followed by a gradual, eventual merger. The night sky would look genuinely extraordinary during that slow approach. As our neighboring galaxy would appear increasingly enormous, its stars spread across an ever-widening region of sky. Earth itself would likely not be endangered by any direct stellar collisions during this process. The greater change would fall upon the overall structure of both galaxies, their disks becoming severely distorted before the combined system eventually settles into an entirely new shape. Our own sun might even be thrown onto a different orbit around the resulting galactic center during the process, a gentle reminder that our galaxy is part of a genuinely dynamic local neighborhood, with a future that includes merging alongside another truly giant system. When galaxies interact, their gas tends to respond far more dramatically than their stars ever do. Gravitational forces disturb huge reservoirs of cold interstellar material, driving clouds into far denser regions, and once enough gas becomes sufficiently compressed, gravity can cause enormous numbers of new stars to form nearly simultaneously. Astronomers refer to particularly intense episodes of this kind as starbursts, and some interacting galaxies produce new stars at rates far exceeding those of calm, ordinary spiral systems. This effect appears especially striking in certain interacting galaxy pairs, where enormous young star clusters have formed during an ongoing merger, many of these clusters containing thousands or even millions of individual stars. The encounter doesn't create this raw material out of nothing. It simply rearranges gas that was already present, pushing portions of it across the threshold needed for gravitational collapse. A galactic collision can therefore look destructive on the grandest possible scale, while simultaneously creating one of the single most productive periods in that galaxy's entire life. Stars behave almost like isolated, well-separated particles when two galaxies overlap, but interstellar gas occupies a far greater fraction of the available space between them. Enormous gas clouds can therefore genuinely collide with one another as two galactic disks pass through the same region, creating shocks that heat some material while compressing other portions into dense layers. This gas also tends to lose orbital energy more readily than stars, since it can efficiently radiate heat away, and as a result, large amounts of material may flow inward toward the center of the merging system, feeding intense new star formation or supplying fresh fuel to a growing central black hole. Astronomers map different molecules to trace this cold material and compare it against hotter gas observed at other wavelengths, revealing exactly where compression is strongest and where new stellar nurseries are most likely to develop. This fundamental difference between gas and stars is genuinely crucial for understanding galaxy mergers. Since a galaxy is never simply a collection of suns, its diffuse material responds through pressure and countless internal collisions, meaning two galaxies can pass right through one another, while their gas undergoes an entirely different and far more turbulent experience altogether. Some galactic encounters create long, sweeping tidal tails containing billions of stars, one of the most spectacular signatures such a collision can produce. During a close passage, gravity pulls more strongly on the nearer sides of each galaxy, stretching material into enormous tails that can reach hundreds of thousands of light-years out into space, carrying along stars that once belonged securely to the galactic disks, together with gas drawn outward during the same encounter. These tails can survive for a surprisingly long stretch of time, since the stars within them continue following related gravitational paths, and their overall shape preserves genuine clues about how the original collision unfolded. Astronomers compare real tidal structures against computer simulations to estimate the direction and timing of past encounters, and some tails even contain active regions of ongoing star formation, where compressed gas has become dense enough to collapse under its own gravity. A galaxy can therefore end up with part of its stellar population pulled into a structure far larger than its original disk, gravity turning a single encounter into a visible record stretching clean across intergalactic space. A galactic collision can sometimes create an entirely new galaxy purely from material torn out of older ones. Tidal tails contain gas and stars drawn outward during an encounter, and in certain regions, gravity can gather enough of that debris into a fully self-bound object, a result astronomers call a tidal dwarf galaxy. Unlike many ordinary dwarf galaxies, these unusual objects form from material that has already been chemically enriched inside far larger galaxies, meaning their gas often contains noticeably more heavy elements than might be expected for a newly assembled system of similar size. Another intriguing difference concerns invisible dark matter, since most models predict that a galaxy's original dark matter remains spread through extended halos, rather than being efficiently pulled into narrow tidal tails, meaning these dwarf galaxies often contain relatively little of it. Their very existence shows that galaxies aren't only created from pristine, untouched material early in cosmic history. Under the right circumstances, fragments torn from already mature galaxies can gather themselves into entirely new, gravitationally bound systems in the aftermath of a collision. When two large galaxies merge, each may bring along a central black hole containing millions or even billions of times the mass of our Sun. The galaxies themselves can settle into a single combined system long before their respective black holes ever finish their own separate journey toward one another. At first, both massive objects move through a crowded sea of surrounding stars, and gravitational interactions gradually rob them of orbital energy, pulling them slowly toward the shared center. Eventually, they can form a genuinely bound pair, though bringing them even closer together requires further interactions with nearby stars or surrounding gas. The final stage occurs only once gravitational radiation becomes efficient enough to drive the black holes rapidly inward, a sequence that can take hundreds of millions of years or considerably longer. Astronomers actively search for galaxies containing pairs of active nuclei as evidence for different stages of this exact process. And a galaxy merger, in this sense, always has an ending hidden deep within its center, long after the larger stellar structures have already blended together seamlessly. A galaxy cluster contains far more than the collection of galaxies visible in any ordinary photograph. Enormous quantities of hot gas fill the space between individual galaxies, and most of a cluster's total mass appears to be invisible dark matter. When two clusters collide, these various components behave quite differently from one another, with the galaxies themselves mostly passing straight through since direct collisions between them remain rare, and dark matter also appearing to pass through with relatively little resistance. The hot gas, however, does not behave the same way, colliding and slowing dramatically as electromagnetic interactions create pressure and intense shock heating. Astronomers can map the gas through its X-ray emission, and separately map the true underlying gravitational mass through gravitational lensing, which measures precisely how background light gets distorted along the way. In some particularly dramatic merging clusters, these two maps simply don't line up, with the dominant mass moving ahead while much of the ordinary hot gas lags behind, offering scientists a genuinely remarkable natural experiment where a single cosmic collision physically separates different forms of matter enough to study each one independently. One of the most famous colliding galaxy clusters owes its scientific importance entirely to this exact kind of mismatch, one that can be mapped directly. X-ray observations reveal where most of the ordinary matter lies, since the collision has concentrated hot gas near the region where the clusters actually pass through one another, while gravitational lensing tells a completely different story, showing the strongest concentrations of overall mass displaced from that gas and remaining closer to the galaxies on either side. Since the galaxies themselves contain far too little visible matter to account for such a strong gravitational signal on their own, another massive, invisible component appears to have traveled straight through the collision without slowing down the way ordinary plasma does. Dark matter provides the standard explanation for this behavior. The observation doesn't reveal exactly what dark matter is actually made of, but it strongly constrains any theory attempting to explain galaxy cluster gravity using ordinary matter alone, nature having effectively separated most of the visible material from most of the gravitating mass, allowing astronomers to compare the two directly within a single system. Galaxy clusters rank among the largest gravitationally bound structures anywhere in the universe, meaning collisions between them involve genuinely staggering amounts of energy. As two clusters approach one another, their vast clouds of hot gas can meet at speeds reaching thousands of kilometers per second, and the resulting collision drives shock fronts straight through plasma that already sits at temperatures of millions of degrees. Some of these shocks extending across distances comparable to, or even larger than, entire galaxies. X-ray telescopes reveal abrupt changes in gas temperature and density marking these moving fronts, while radio observatories can detect enormous diffuse structures that often trace regions where particles have been accelerated by the merger shock itself. Unlike the sharp, sudden blast from a single stellar explosion, A cluster collision unfolds gradually over hundreds of millions of years, its scale almost impossible to mentally grasp, since light itself may take millions of years just to cross the affected region. These events demonstrate that cosmic violence certainly isn't limited to compact objects alone, since entire collections of thousands of galaxies can collide and send pressure waves rippling through volumes of space large enough to engulf our own galaxy many times over. The universe contains natural particle accelerators vastly larger than anything humanity has ever managed to construct. Shock waves and powerful magnetic fields generated by supernova remnants, colliding galaxy clusters, and relativistic jets can repeatedly scatter charged particles, with each interaction potentially increasing a particle's energy until it eventually travels at a speed extremely close to light itself. The exact acceleration mechanisms involved still vary, and researchers continue debating which sources dominate at the very highest energies. Though one widely studied process involves charged particles crossing back and forth through a shock front, while magnetic turbulence repeatedly redirects them, allowing for gradual, repeated energy gains. Because astrophysical shocks can span enormous distances and persist for extremely long periods, they can push particles to energies far beyond anything achieved inside terrestrial accelerators. These particles eventually escape and may travel through interstellar or even intergalactic space before encountering matter somewhere else entirely, their paths bent along the way by magnetic fields, which makes tracing their true origin genuinely difficult. A cosmic collision can therefore become a kind of natural machine, launching individual atomic nuclei clean across the universe at energies human technology has simply never managed to directly produce. For only a few thousandths of a second, a distant, otherwise unremarkable source can briefly become one of the brightest radio objects in the entire sky. These extraordinarily brief flashes were first recognized after astronomers noticed an unusual pulse buried within archived telescope data, and large surveys since then have gone on to detect hundreds of similar sources. Despite their extremely brief duration, some release as much radio energy in that single instant as our own sun produces across many entire days at every wavelength combined. Their short duration alone shows that the emitting region must be remarkably compact, since a source simply cannot vary coherently faster than light itself could cross the region responsible for that change. Early examples proved difficult to interpret precisely because radio telescopes often provided only rough positional estimates. But newer instruments can now pinpoint some events down to individual host galaxies, a breakthrough that proved many of these mysterious flashes originate far beyond our own galaxy entirely. Whatever the detailed explanation turns out to be, these signals demonstrate that a tiny region of space can release an astonishingly concentrated burst of radio energy and then vanish again, almost immediately. Some of these fast radio bursts repeat, firing off pulse after pulse, while others appear to flash only a single time and never again. The discovery that certain sources genuinely fire repeatedly transformed the entire mystery surrounding them, since a repeating source clearly cannot be explained by any event that completely destroys its own engine during the very first burst. Some repeaters have already produced dozens or even hundreds of individual pulses, with intervals ranging anywhere from mere seconds to entire months, and their individual bursts can differ considerably in brightness and duration. In several cases, periods of activity even appear to follow longer underlying cycles, though the reasons for that pattern remain genuinely uncertain. Other sources have never once been observed to repeat, despite extensive ongoing monitoring, a distinction that may point towards several genuinely different classes of physical origin, or may simply reflect the limits of current observational technology. Astronomers compare burst shapes and local environments carefully, searching for patterns, since two flashes that look nearly identical through a telescope might come from related engines behaving somewhat differently, or from entirely separate cosmic processes capable of producing the exact same brief radio signature. Magnetars remain the leading explanation for many of these repeating radio flashes, since a magnetar possesses exactly the sort of extreme physical ingredients capable of producing a powerful radio flash from an extraordinarily small region. Its immense magnetic field stores enormous amounts of energy, and sudden internal rearrangements can rapidly accelerate charged particles. Researchers have developed several competing models in which magnetic activity either launches disturbances into the surrounding environment or directly produces coherent radio emission near the star itself. The repeating nature seen in many of these sources fits this picture quite naturally, since a magnetar can easily remain active well after each individual outburst. Young magnetars may be especially promising candidates if they happen to be surrounded by dense leftover material from their own formation, an environment that could help explain why some repeaters display particularly complicated radio behavior. Not every detail has been solved, and astronomers still debate exactly where the radio waves themselves are actually generated, and why only certain magnetars appear capable of producing exceptionally luminous bursts. Yet the overall connection between the strongest known stellar magnetic fields and some of the shortest, brightest radio events ever detected remains genuinely compelling. In the spring of 2020, astronomers finally caught the confirmation they had long been waiting for. A magnetar residing within our own Milky Way galaxy produced an intense burst of radio waves that, viewed from another galaxy entirely, would have closely resembled a relatively faint fast radio burst. X-ray instruments detected corresponding high-energy activity at nearly the exact same moment, strongly reinforcing the connection to magnetar outbursts. This marked the very first direct demonstration that a known magnetar could genuinely produce a radio flash approaching the extraordinary class of events previously detected almost exclusively at far greater extragalactic distances. The event didn't prove that every single fast radio burst originates from a magnetar, only that magnetars are capable of producing at least some of them. Researchers studied the timing and structure of this particular pulse in extraordinary detail, since the source sat far closer than typical examples of the phenomenon, turning a broad theoretical possibility into a genuinely observed physical link. A mysterious phenomenon first discovered far beyond our galaxy, suddenly revealed to have a recognizable relative living quietly right here within the Milky Way. A fast radio burst carries information not only about its actual source, but also about every cloud of ionized matter it happened to encounter along its long journey toward Earth. Lower radio frequencies travel through free electrons slightly more slowly than higher frequencies, meaning the burst arrives spread out across time in a predictable and measurable pattern. Astronomers measure this effect through a quantity known as the dispersion measure, part of the resulting delay coming from electrons within our own Milky Way, with additional contributions arising from the host galaxy itself and from material near the source. Whatever remains can trace the otherwise elusive material scattered between galaxies, which matters enormously, since much of the universe's ordinary matter is believed to reside in diffuse gas that is extraordinarily faint and difficult to observe directly. By combining a burst's dispersion measurement with its independently determined distance, researchers can estimate how many electrons lie along that particular line of sight, meaning a well-studied population of these bursts can effectively map the distribution of ordinary matter across enormous stretches of cosmic space. A single millisecond flash becoming a genuine measuring probe for material too thin and diffuse to glow brightly on its own. By the time a particularly distant fast radio burst finally reaches Earth, the galaxy that originally produced it may have changed almost beyond recognition. Radio waves from certain sources have traveled for billions of years across an ever-expanding universe before finally striking a telescope for only a handful of milliseconds. During that immense journey, cosmic expansion stretches the wavelength of the signal, while intervening plasma further alters its arrival pattern. Astronomers can identify a host galaxy for well-localized bursts and measure its distance, allowing them to connect the observed pulse with a very specific period in cosmic history, and particularly distant examples give researchers a genuine way to study how intergalactic matter has evolved over enormous stretches of time. The contrast in timescales here is genuinely extraordinary, the source having emitted its defining signal in a fraction of a heartbeat, only for that radiation to then spend a significant portion of the universe's entire history traveling toward us, crossing enormous regions of space, while entirely new stars formed and died elsewhere along the way. Radio astronomy compresses that whole journey into one brief trace on a detector, a single momentary event arriving carrying information gathered across billions of light years. Earth is continually bombarded by atomic nuclei and other particles arriving steadily from space. Most of these cosmic rays carry relatively modest energy by astrophysical standards, but a tiny fraction are astonishingly powerful. The very most energetic examples carrying far more energy within a single particle than our largest human-built accelerators can give to an individual proton. When one of these particles strikes our upper atmosphere, it collides with an atomic nucleus and creates a cascading shower of secondary particles that can spread across many square kilometers before ever reaching the ground. Large observatories detect these showers using extensive arrays of particle counters or telescopes tuned to catch the faint ultraviolet light produced within the atmosphere itself. The original cosmic ray never actually reaches any detector intact. Researchers instead reconstruct its energy and direction purely from the enormous cascade it leaves behind. These events remain genuinely rare, especially at the very highest energies, meaning detecting enough of them requires observatories covering truly vast areas, nature somehow accelerating a single atomic nucleus to energy levels beyond our most powerful machines, then sending it across space until Earth's own atmosphere finally becomes the target that reveals its arrival. Astronomers know for certain that these ultra-high energy cosmic rays exist, yet tracing them back to their original source remains exceptionally difficult. Charged particles simply don't travel through the universe in perfectly straight lines since galactic and intergalactic magnetic fields bend their trajectories considerably, erasing much of the directional information that ordinary light would otherwise preserve. At the very highest energies, this deflection does become somewhat smaller, offering researchers some genuine hope of eventually identifying source regions, and observatories have already found hints of possible associations with certain nearby extragalactic structures, though no single population has yet convincingly explained everything observed. Possible accelerators include active galactic nuclei and other environments capable of sustaining truly immense electromagnetic fields. There's an added complication too. Since the very highest energy particles interact with background radiation during their long journeys, limiting how far many of them can actually travel without losing energy, meaning their sources simply cannot lie arbitrarily far away. Somewhere within the relatively nearby universe, natural machines are quietly accelerating atomic nuclei to truly extraordinary energies, yet the precise identity of those machines remains one of the most persistent mysteries in modern high-energy astrophysics. At the center of an active galaxy, matter falling toward a supermassive black hole can help create jets extending far beyond the visible galaxy itself. These outflows may travel for hundreds of thousands, or even millions, of light years before finally slowing down, and radio telescopes reveal enormous glowing lobes where the jets ultimately deposit their energy into surrounding space, the particles within them radiating strongly as they spiral through powerful magnetic fields. One remarkable system can therefore contain a central engine smaller in scale than our own solar system, while simultaneously producing structures considerably larger than the entire galaxy hosting it. These jets remain surprisingly narrow even across vast distances, which suggests that magnetic fields play a major role in guiding the flow, and they can also develop bright knots and hotspots wherever the material encounters resistance. Astronomers study these enormous structures to understand exactly how energy from a galactic nucleus reaches its surrounding intergalactic environment, a black hole defined by its ability to trap anything crossing its horizon, and yet capable of producing some of the longest coherent structures visible anywhere across the entire cosmos. Quasars are powered by rapidly feeding supermassive black holes, and not all of the infalling material actually reaches the black hole's horizon. Radiation and magnetic processes can instead drive tremendous winds directly away from the central region, with spectra revealing gas racing outward at thousands, or even tens of thousands, of kilometers per second. If enough material participates in this outflow, it can carry an enormous amount of energy straight into the surrounding host galaxy. Astronomers suspect these winds represent one important way that black hole growth can influence star formation far beyond the immediate nucleus, since gas compressed by such an outflow might trigger new stars to form in some locations, while elsewhere that same wind could heat or strip away the cold material needed to form future stars entirely, an interaction known broadly as feedback. Modern galaxy evolution models often require some form of powerful feedback like this to explain why the very largest galaxies don't simply convert all their available gas into stars. A black hole occupies only a tiny central region, and yet the energy released while it feeds can influence gas located thousands of light years away, meaning the consequences of its activity can genuinely spread across an entire galaxy. The energy released around a supermassive black hole can produce completely opposite effects depending on exactly where and how it reaches surrounding galactic gas. A powerful jet may plow directly into a cold gas cloud and compress it until gravity finally triggers new star formation, and observations have indeed found systems where star formation appears noticeably enhanced along a jet's path. In other environments, the outcome runs in the opposite direction entirely, since jets can inflate enormous cavities within the hot gas surrounding massive galaxies and clusters, and the injected energy prevents that gas from cooling efficiently enough to ever settle into new stellar nurseries, meaning star formation slows dramatically without a fresh supply of cold material. This balancing act sits at the center of modern ideas about galaxy evolution. The black hole itself never intentionally regulates anything. Energy released during its feeding simply changes the physical conditions around it, yet the overall result can resemble a thermostat operating on truly galactic scales, the very same basic engine capable of encouraging new stars in one region while preventing their formation somewhere else entirely. A blazar isn't a fundamentally different kind of galaxy at all. It is simply an active galactic nucleus, viewed from an extraordinary angle, with one of its relativistic jets happening to point almost directly toward Earth. Because the emitting material moves close to the speed of light, relativistic effects dramatically enhance the observed brightness and make its variations appear unusually rapid. A blazar can flare dramatically across radio, optical, X-ray, and gamma-ray wavelengths all at once, some changes occurring on timescales short enough to prove that the emitting region is remarkably compact. Its radiation is also often strongly polarized, revealing the influence of organized magnetic fields woven throughout the jet. Astronomers monitor these objects closely, precisely because their violent variability offers a direct window into the behavior of relativistic plasma, and high-energy neutrinos have even been associated with at least one flaring blazar, raising the intriguing possibility that these jets are capable of accelerating particles to truly extreme energies. Change the viewing angle even slightly, and the very same object might appear considerably less dramatic. Blazars demonstrating quite beautifully that perspective alone can determine whether a distant galactic nucleus looks perfectly ordinary or becomes one of the very brightest high-energy sources in the entire sky. Two white dwarfs locked together in a tight binary system can spend ages slowly spiraling toward one another before their final, dramatic encounter. If the combined conditions allow carbon burning to ignite catastrophically during that final merger, the result may be an especially bright thermonuclear supernova. This particular scenario stands as one of the leading proposed pathways for producing these vitally important explosions, with the finer details depending heavily on the masses and compositions of the two remnants involved. In some mergers, one white dwarf may be disrupted first, forming a hot structure around its companion before ignition even occurs, while in others, violent compression during the collision itself could trigger burning almost immediately. Astronomers search for supporting evidence by examining supernova remnants and looking for any surviving companion star nearby, since a genuine double white dwarf merger should leave no ordinary donor star behind at all. Understanding exactly which pathway is correct matters far beyond simple stellar evolution, since these explosions serve as some of astronomy's most valuable cosmic distance markers, meaning some of our most trusted cosmic rulers may quite literally begin with two apparently dead stars finally colliding. A thermonuclear explosion differs fundamentally from an ordinary core collapse supernova. Rather than gravity crushing a stellar core down into a compact remnant, runaway nuclear burning can instead release enough energy to completely unbind a white dwarf. When two white dwarfs collide or merge under the right conditions, carbon and oxygen may ignite across a substantial fraction of the combined material, with burning racing through the dense stellar matter and converting it into heavier nuclei while releasing enormous amounts of energy. If the resulting explosion proves sufficiently powerful, no neutron star gets left behind at all, since the original white dwarfs were never massive stellar cores undergoing true gravitational collapse in the first place. Their matter is simply dispersed entirely, Astronomers test this picture by searching old supernova remnants for any sign of a compact central object, and the absence of one is generally consistent with a thermonuclear origin. The expanding debris eventually mixes into interstellar space, enriching future generations of stars with elements such as iron, two stellar corpses meeting long after their original stars have already faded, experiencing a second, final ending so complete that neither one survives the encounter as any kind of bound object. Direct stellar collisions remain quite rare across most of an ordinary galaxy, but the situation changes considerably inside exceptionally dense star clusters. Near their centers, thousands or even millions of stars may occupy a relatively small volume, continually passing one another along complicated, overlapping orbits. Over long stretches of time, chance encounters can occasionally become close enough for stars to genuinely touch or merge, and gravity can also help focus their trajectories, increasing the effective collision rate even further. The result may produce a star more massive than would normally be expected within an old, established cluster. One particular population of unusually young-looking, hot stars found in old clusters is believed to form through exactly this kind of merger or interaction, appearing noticeably younger and hotter than the surrounding stars around them despite belonging to the same aging population. In especially extreme environments near galactic centers, repeated collisions could potentially build unusually massive objects over time. Most stars, of course, live out their entire existence without ever touching another sun. Yet in the very densest cosmic neighborhoods, sheer crowding can eventually turn a near-impossible event into a genuinely important part of stellar evolution. There is something wonderfully clarifying about following all of this back to a single idea. The universe's greatest catastrophes repeatedly turn out to double as engines of creation. Stellar explosions return chemically enriched material back out into space, allowing later planetary systems to contain elements that earlier generations simply never had access to. Galactic encounters can compress gas and spark immense new populations of newborn stars. Colliding neutron stars manufacture nuclei that ordinary stellar interiors could never produce on their own. Even the restless activity swirling around black holes can redistribute matter and quietly influence which regions of a galaxy go on to form the next generation of stars. None of this makes the underlying destruction any less extreme. Stars are genuinely erased. Galaxies are genuinely distorted beyond recognition. Matter is thrown across distances too vast for the mind to properly hold. And yet cosmic evolution depends entirely on that continual recycling. A universe where matter remained forever locked inside, only the very first generations of stars would look nothing like the rich, complex ones surrounding us tonight. Much of what exists now, including the quiet room you're resting in, only exists because earlier structures were broken apart long ago, their material gathered up and used again. Catastrophe and creation, out there among the stars, are never really opposites. They are simply consecutive chapters of the very same unfolding story, the universe patiently building new possibilities from the remnants of events powerful enough to destroy whatever came before them. And with that gentle thought, we arrive at the end of tonight's quiet journey through some of the most extreme corners of the cosmos. We have followed dying stars through their final, blinding moments and watched entire galaxies slowly reshape themselves under gravity's patient pull. We have seen matter pressed into states that shouldn't exist, while distant collisions sent their whispers traveling across space for billions upon billions of years. Some of these events lasted less than a heartbeat. Others unfolded across stretches of time so vast that no single human life could ever witness their beginning and their end. And yet, from right here on this quiet small planet, we can still detect them. Their light still reaches us out of the darkness. Their radio signals still arrive gently at our telescopes. Their gravitational waves still pass silently through the ground beneath you, right now, as you rest. But for tonight, you can leave every bit of that far behind you. Let the distant galaxies continue their slow, unhurried drifting through space. Let the stars keep following paths they have already been tracing for millions upon millions of years. None of it needs your attention any longer. Let your breathing settle into something slow and easy. Let your shoulders soften a little further into whatever is holding you. Feel the quiet weight of your own body, resting, supported, safe. Let the small, restless thoughts of the day grow softer, further away, less important than they seemed only a few hours ago. If this quiet wandering through the stars helped you settle tonight, You're always welcome to come back and drift along again another time, but there is nothing more you need to do right now. Nowhere else you need to go. No thought you need to finish. Just let go, a little more and a little more still. Rest well now. Sleep deeply, and good night.